Actually, what I might do here before we get into the homework might not be um, a bad time to just run through something we did in class, I think last Thursday. I'll throw this up on the screen and then we'll go through it here in a little bit. So you don't have to write this down. You may have written it down already. We'll go through and when we start reviewing, we'll go through some of these things. Um, on Thursday, now we did some new stuff on Friday, but on Thursday we said, okay, we've got these limit problems. The long way is the first thing we got, this limit definition of the derivative. The limit definition, or just the definition of the derivative, is this thing here. We just pretty much have to have that memorized. Know what that looks like. Okay? On your worksheet, some of that stuff you've had access to that. You need to memorize this. If it says the definition of the derivative, you've got to know that you set your limit up like this. And we'll practice on here. Okay? Then we had this shortcut rule for power derivatives. And then we've used that now for some local max min, some of that stuff. And there could be some problems where you just have to do the shortcuts. You have to know that x square root of x is x to the 1/2 power. Stuff like that. Okay, then we've done a whole bunch of stuff with limits. And we'll go over your worksheet here quickly here a little bit. The tables, doing a table, that will be a part of the quiz. Basically, that's about all we've done on the calculator. So the calculator part of this quiz, again, will probably be the shorter part of this. It'll focus on the calculator tables. All right. We had some problems where I gave you a graph, piecewise, all broken and jumps and all kinds of things like that. And we talked about limits, do the cars meet, that kind of stuff. And then we also had the worksheet where we had to do the algebra. So we're gonna do some of those today with the conjugate, the common denominator, and stuff like that. 0 over 0 means you keep going, try to get some stuff to cancel, that kind of thing. Then we did chart stuff. Okay, we did chart stuff, local max min, increasing, decreasing, stationary points. That's where we did the use your derivative rules, set it equal to 0. 54 was really a chart problem today. 54, we'll go over that one. Okay, 52 a little bit was a chart problem as well. Okay, it was one of these kind of local max min, increasing, decreasing kind of things. Okay. And then there was number 19. That was when we worked out that chart problem, and I think that's about it. Okay? So, now what isn't included here would be what we did on Friday. Let me pull that up here. Our notes from Friday when we talked about a table. We talked about no matter what's in here, right? Our limit is where these are approaching. Now, the way this table's written right now, if you were gone and looked at these notes, it might have been a little confusing unless you watched the video. The way this table is written right now, what would you say the limit is as x approaches 3? Does not exist. Because on the left, less than 3, it's negative 5.371. To the right of 3, it's positive 5.371, so the cars wouldn't be meeting. Now, when we first did this table in class on Friday, I had these all positive. So these were positive, so the limit was 5.371. And we don't care what's here. We got a German short hair there now. But there was like a 21 there. Even if there's a 21 there, it doesn't matter. The limit would still have been the 5.371 or does not exist, but the 21 doesn't have anything to do with it, or the German short hair doesn't have anything to do with it. Okay, when we do our table. All right, so we talked about that. Here was another one of those chart problems with our number line, so we'll go through that again today, because that is a part of the quiz. We want to be able to do that. Here was the new thing we learned on Friday about when a function is continuous. Now, this gets to problem 66 and 67. Okay, is a function continuous? It's continuous at a point if the function is defined there, means if you have an output, right? So this is what we wrote in our notes. This doesn't have an output, it's got a hole. This doesn't have an output, it's got a vertical asymptote. The limit has to exist. The cars have to meet, so you couldn't have a break like this. And the limit has to equal the output. The cars have to meet where the diner is. The cars have to meet where the output is. If those are different, then again, it's not continuous. So continuous is anything that would cause you to kind of have to lift your pencil off the paper because of a hole or something like that. So it has to be all those things be continuous. And then we added the idea that it's differentiable. Differentiable says, okay, it's got to be all those things. It's got to be continuous. Never have to lift your pencil, and can't have any sharp points or vertical tangents. You never lift your pencil on these. So these are continuous, but they're not differentiable. Because you have a sudden change, like a sharp point, or you have an undefined slope, the derivative does not exist. So if the derivative does exist everywhere, and it's continuous, then we say it's differentiable. And the word you'd want to associate with differentiable would be smooth. Not only is it never lift your pencil, but it's also smooth. Okay, now I suppose that would fall apart here. This seems pretty smooth as well. Okay, but it does have a vertical tangent. It is, the slope is undefined here. So even the word, whenever we try to do these informal words and make it a little easier on ourselves, sometimes it doesn't tell the whole picture, so we do have to be careful. So even smooth wouldn't necessarily cut it all completely. All right, so there you go. And then this would be the one thing, this antiderivative thing is probably the one that I'm going to tell you don't worry about for the quiz. The next quiz we do, which might be before Thanksgiving, we'll get into a few more antiderivative type things. Okay, so we do have a pretty rugged stretch here, about 7 days here, where we might have 2 quizzes. Okay, so and part of that is probably it should be a good thing, because otherwise then we have to kind of do a quiz after Thanksgiving of stuff that we did before Thanksgiving, and then that's kind of a long gap. So that's probably what we're going to do. We're probably going to have another quiz at on that Tuesday before Thanksgiving, just so we can get that kind of done while it's a little more fresh. That's kind of the tentative plan, but let's don't worry about that right now. Okay. This antiderivative stuff, we'll go over a couple of those homework problems, talk about just a little bit, but for the most part, you won't have to worry about them for tomorrow's quiz. Okay, antiderivative. So that, in kind of a nutshell, is the big picture of everything we need for the quiz. So let's go through and let's see some examples of those various things. So let's get into the homework. Maybe if we start with 66 and 67, we can start right here with this. Matter of fact, why don't we start with 31 through 34, because those are the ones I said we don't have to worry about as much, so let's get those out of the way. So these actually should have been a little easier than you may have made them. If you thought they were pretty easy, you probably were thinking of it right. If these problems are really just about the notation. Okay, we talked about big G is the antiderivative of little g. And so, is this an antiderivative of this function? There'd be 2 ways to do it. One way would be to do what? Do the derivative of big G. That's the easiest way. So is this an antiderivative of this? Well, do the derivative of this, see if that's what you get. So, do the derivative of 3x squared, 4 would go away. Is that? No. Somebody in the other class said, well, could you just do the antiderivative with the rule we learned, where you raise that up to a 3, divide by 3, and then plus some constant? And you could. That'd be 1/3 x cubed. You look over here. Oh, there's no 1/3, so it's not right. Okay, same thing here. Remember, square root is 1/2 power. So this would be x to the 3/2. Let's do the derivative. Bring the 3/2 down. It'll cancel the 2/3. Drop the 3/2 power by 1, it'd be 1/2. This would be x to the 1/2. The 4 would go away. Yes, it matches. So this is an antiderivative of that. Okay? Then they ask you on 33, they said, suppose the big G is this, and big G prime equals G. What did they just tell you right there? No. Well, yeah, little g equals G, but that G is the antiderivative. What they just told you, if big G prime is the same as little g, what they just told you is big G is the antiderivative of little g. Instead of like in 31 and 32, they just said something about it, or they asked if it was. Sometimes they could just say big G is the antiderivative of little g, but most of the time they'll just write this. That's what that tells you. Because think how we check these. We did the derivative of big G and saw if we got little g. So if you do the derivative of big G and get little g, that means big G is the antiderivative. So that's what they told us. Big G is the antiderivative. So then they say find 3 antiderivatives of little g. Well, there's one. Right there. They gave it to you. What's another one?
Plus 1.
Plus 1. Minus 1. There you go. So there's 3. So if you look at that, you think, well, yes, that was dumb. Well, no, not really, because you had to understand the notation to know that's what they wanted. So it was just a question about notation. Okay, same thing is true here. Big F prime is equal to big G prime. Is it possible that this is true? Yes or no? The answer is no. Somebody who said no want to explain why it's no. Well, it's no, that's not really shift to the left. It's not so much that, but it's, if it's any kind of shift, it'd be more of an upshift. But it's a simple, let's see, how can I say this? When we did our 3 antiderivatives here, big G was this one. Another one would be a plus 1. Another one would be a minus 1. What's the difference between all of those? Just a constant. Just a vertical shift of a constant. So 2 antiderivatives, and that's really what we're saying. If big F prime is equal to big G prime, that says that big F and big G are both antiderivatives of the same thing, right? If you do the derivative of big F and do the derivative of big G and get the same thing, then they're both antiderivatives. So the only difference between them can be what? A constant, the plus 4, plus 5, plus 6. Well, is that the only difference between big F and big G here? No. If this was a plus 7, then that would be true. If this was plus 7 or minus 2 or something like that, then this would be a true statement. The other way to do it is just do the derivative of both sides. Do the derivative of both sides of this thing right here. What's the derivative of big G? Big G prime. What's the derivative of this side? Be big F prime plus, what's the derivative of x? 1. So this would say big G prime is equal to big F prime plus 1. Can that be true? No, big F prime has to be equal to big G prime, not equal to big G prime plus 1 or big F prime plus 1. So, again, let's don't worry too much about that. We'll get into that a lot more. That'll make a lot more sense later on, I think, as we talk about that antiderivative idea more and more as we go forward. But that stuff I'm not really going to get into in this quiz. All right, so now let's move on to 66 and 67. Now, basically what you have there is a piecewise function, and this is asked a lot on, I was looking for one in our practice tests that we do getting ready for our midterm and final, and I just pulled up one here, and I didn't find one exactly like that, but I did find some other good problems, so I thought we'll look at those here in a minute. But so let's just take a look at this one. When you're given a piecewise function, on this particular one we have what? Ax plus 1 and x squared. And x is what, less than 2? And here it's greater than or equal to 2. Okay? On the AP test, in the multiple choice section, they love this kind of problem when it comes to continuous and differentiable functions. All right. But it's important to just understand what they're asking here. And you guys, I'm not sure you noticed it, but in 66 and 67, they're asking exactly the same 2 questions. Part A of both of them is exactly the same, and Part B of each of them is exactly the same. Now, I'll show you in a minute what I mean, because they word it completely different. In 66, they ask, make the limit as x approaches 2, make it exist. Find A so that the limit will exist, right? That's what they ask in 66A. Well, let's think about what we have here. I have no idea if this is right. As a matter of fact, I'm pretty sure it's not. But what we have is what kind of graph right here? Line. And then well, what could possibly happen? Well, I could have the line take off and do this, and it doesn't include the 2, right? So the line could stop right there. I know that's not what that line does, but let's just say it does. And then after the line stops at 2, I got a parabola that starts. So let's say I got a parabola that goes like this. Okay, I know that's not what that parabola looks like, but let's just pretend. All right? So would the limit exist there? No. What would we have to do to make the limit exist? I got to bring it down. So what? So that this output and this output are the same when x is 2. So what do? You plug a 2 in for x, which on this one would be 2a plus 1, and on this one would be 4, and those two have to be equal to each other. It's that simple. That's all you do. But, I mean, you had to understand what they're asking. So for the limit to exist, the two y values there had to be the same when x was 2. So we plug the 2 in for x, we subtract a 1, okay? A would have to equal 3 halves. Okay? Now, let's look at 67. 67 is very similar. It's got a line. I think it's got a line and a parabola also, right? Except it's parabola first and a line. It says that f is a continuous function. And then in part A it says find A. Okay? It's the same thing. Is this continuous? When it's split like this? What would make it continuous? If it was together. It's the same thing. It's the same question. Right? If this was together. If you plugged a 2 in for x, these two y values would have to be the same. So you do exactly the same thing in 67A. Except is it a 2 where they break? Yeah, it is a 2 where they break. So you put a 2 in for x, you set the two of them equal to each other, and you find A. Same exact question. All right, now, let's do part B. What's part B say on 66? It says, if A has the value found in part A, does f prime of 2 exist? So let's say we now have made this so that they're equal. What makes the derivative exist? Now, I might not have done a very good job there. Let me make my parabola do that. If this black graph here is now my graph, does a derivative exist there too? The way I drew it. Why not? Sharp point, because there's a sudden change in slope. To be differentiable, the slope of the line here has to be the same when it goes out. In other words, it has to be smooth, so there's no sharp change. In other words, not only do the y to be differentiable, not only do the y values of the two have to be the same, but what else? The slopes have to be the same, which means the derivatives have to be the same. So what you do is you take this one and do its derivative. Now we said we have 3 halves in there now, right? We just found A was 3 halves. So this function is 3 halves x plus 1. What's its derivative? Just be 3 halves, right? What's the derivative of this one? 2x. But then we got to plug a 2 in for x, right? So because we're talking about at this point. So if we plug a 2 in for x, is it differentiable? Does f prime exist then? That means the line has a slope of 3 halves, but the parabola, when it takes off at 2, has a slope of 4, much steeper than 3 halves. There's going to be a sharp kind of point there. The slopes are not going to be the same. So it is not differentiable. Now let's look at what 67b says. 67b says, is f differentiable at 2? It's the same question. Is f differentiable at 2? So you do the derivative of each of those. You already found A in part A. So you plug A in there. You do the derivative of each part. You plug a 2 in for x. You see if they have the same slope. If they have the same slope, then it's differentiable. So continuous means they have to have the same y value at that point. Differentiable says they have to have the same slope at that point. Okay? So 66 and 67. Now, while we're on this limit idea, before we move on to 52 and 54, let's talk, let me pull up some example problems here. So all of these that we're doing right now are good examples to be studying for the quiz tomorrow. This idea of continuous and differentiable, okay, being able to understand this. Now I want to go to a sample, one of our practice exams that we'll be working on later this year. And there was a good problem in here about continuous and differentiable. I think this was the one I was looking at. Yeah, there's a couple of them. Here's one right here. Now, I'm not saying these are exactly ones that, like, we'll have to do. This one is probably not like one we have to do, but certainly could be. It very well could be on the next quiz. Just read that one real quick. Now, this is a no calculator. Anybody got any thoughts there? F prime of 2. You know, a week or two ago, I started class one day with a problem where I said, let's list all the different ways we can find F prime of 2. Remember that? There's F prime of 1. I don't remember what it was. But let's go through that again. So what are all the, here's a function. What are all the different ways you can find F prime of 2? The long way, that we could write out that whole definition of the derivative, right? What is that? Limit h approaches 0, f of, in this case it'd be 2 plus h minus, right? That's good practice. And then what would we do for the next step? We plug in a 2 plus h in for x. We have 3 plus, what would that be? 2 plus h minus 2 minus f of 2 all over h. Now this one actually works out decent, but you know, sometimes, this is another thing, another example I'm going to work out for you here in a little bit. Sometimes we get to where there's no algebra we can do. You know, and then what do we do? If there's no algebra, let's see what happens here. It looks like the 3's are going to cancel. 2's are going to cancel. Clean up with that. The problem is that's still 0 over 0. Can those h's cancel? Not really. Now we could probably think our way through this one. Let's wait until we look at it some other ways and then come back to this one, because I don't expect you to do one like this, to be honest with you. I think this would not be the best choice for this one, okay? But actually it doesn't work out too bad, but you do have some thinking you have to do here that I'm not requiring you to do, okay, right now. So what's another way? So one way is a long way. What's another way to find F prime of 2? Calculator table, but this is a no calculator, because right here we could graph this, right? Think of your calculator table, the ones you did on the worksheet today, right? What would you do? You'd grab this one and graph it right now, right? Except you couldn't use h, you'd use x, right? And we'd look as x approaches 0, right? We're not looking at the 2, right? The 2 doesn't have anything to do with it. We're still on our table, look at this, so we could do that, right? Okay? But this is a no calculator one, so that wouldn't be a good option. But I might, if I gave you a complicated function that you couldn't do algebra to, I might exactly expect you to do that. I might put it on the calculator section. Set up your definition, then go to your table. We'll do one of those here in a minute. Okay, so what's another one?
Can we just think about what the graph might look like?
How about think about what the graph might look like? If it's one you could picture a graph like in chapter 1, maybe you can get the slope from that. Okay? What about a derivative rule, like our shortcuts? Do we have a shortcut rule, though, for absolute value? I don't think we do, right? So that wouldn't work very good. So let's go with what Brandon was saying. Is this one we should be able to look at a graph?
Yeah.
What's absolute value graph?
It's a V.
V. What's a minus 2 mean?
Shifted right 2.
Right 2, up 3. This is the way they really intended you to do this one. It'd be much quicker, especially on the AP test where time is kind of at a premium on some of these. You just think of the V graph. This is just 2 to the right, up 3. What's the slope at 2? Undefined. And that would have been by far the easiest way to do it. Now, let's come back to the red one here. absolute value of h as h approaches 0. Well, if h approaches 0, what if h is negative as it approaches 0? Then you'd have positive h over a negative h. What's that? Remember, h is the same, what's h divided by h? 1, but the top one's positive, bottom one's negative. That'd be like 3 over negative 3. What's that? Negative 1, right? What if the car is approaching from the right, approaching 0 from the right, the positive? You have positive over positive, which is 1. Oh, so it'd be negative 1 on the left and positive 1 on the right. Well, they don't meet, so it doesn't exist. What's the slope on this side? Negative 1. What's the slope on this side? Positive 1. See how that would give you negative 1 and positive 1? Same thing. So we could have actually done it. It would have kind of worked there, but it would have been much longer than we needed to. Okay? So they really wanted you to just do a graph and then go from there. Okay, here's another one that's kind of related to that idea of continuous and you have to do limits and stuff. Here's a graph. I better shrink that down. Okay? Here's a graph. So this is definitely going to be something I'm going to give you. We did a lot of problems like this, give you this kind of funky looking piecewise function, and ask you some questions here. Which of these following statements is true? Limit as x approaches 3 equals 1. True or false? As x approaches 3, the cars meet at 3. So that is false. As x approaches 4, the limit is 3. What's the limit as x approaches 4? Does not exist. This car is down here somewhere. This car is up here at 3. Limit does not exist. Cars don't meet. So we haven't found one that's true yet. Is f continuous at 3? Now, in our notes Friday, we had 3 reasons for being discontinuous. On the quiz, I may ask you, is this function continuous at 3? And if the answer is no, you have to tell me why it's not continuous. So let's do that. So tell me why, using one of those 3 reasons from Friday, why is it discontinuous at 3? It's not undefined because at 3 it does have an output. They're not equal. It's the third one. The limit doesn't equal the output. The limit is 3. The output is 1. So it fails the third in our list of 3 things. But don't say the third one. Say the limit as x approaches 3 does not equal f of 3. Is f continuous at 5? Sharp point, but does that matter for continuous? No, it's not differentiable at 5, but it's continuous at 5. Yeah, you don't lift your pencil, the output's there, the cars meet there, everything's satisfied. So there's the one we're looking for here, it's true. Okay, and then let's just look at this one. Does the limit as x approaches 6 equal f of 6? No, f of 6 is down here at 1. The limit doesn't exist because the cars don't meet. Okay, so here's one that in May, in April, whatever we're going to be looking at, well, in February we're doing a midterm, and we'll be coming back and we'll be seeing some of the same stuff. Okay? So, let's do one other one. This relates to limits. This was problem number 1 on this practice test, right here. Again, no. Yeah, but there's like 50-some questions, and maybe 3 of them we can do, and the rest we can't do, and you know what I mean? It would just be, it would just be. I just had to randomly kind of go through here and find a few that looked good. What about this one? Limit as x approaches b. What's the first thing you have when you have a limit problem? And the directions, I'd probably help you a little. The directions say find these limits, use substitution, algebra, etc., whatever. So you plug in a b first, right? Should plug in a b. Do substitution first. B minus b, 0. Square root of b minus square root of b, 0. 0 divided by 0?
Undefined. Guys.
Indeterminate. It is undefined, but what do you do if you get 0 over 0? You keep going, right? You keep going. And you do what? Well, what are you going to do on this one? Conjugate and cancel. Conjugate and cancel. We got common denominator, we got conjugate, and we got factor and cancel. Okay, do it on your paper real quick. do conjugate and cancel to this one. Having trouble getting started? Anybody getting one of those? A, B, or C? Or D, or E? None of the above? I know I covered them. Oh, you can't see them. Hang on. Oh, I froze it. I'm sorry. There you go. Anybody? A, B, C, D. A. It is A. Okay? So you multiply by the conjugate. And it's the radical one that you're focusing on. The conjugate method, right now, the only time we're using it is when we see the radical. Okay? What do you get on the bottom? Well, you get x minus b. The outers and inners drop out. Now, can we cancel those? We take out a negative. Remember, we had that one with 9 minus x on the worksheet the other day. Okay? Now, we can cancel the x minus b, which leaves us then with that. What do you do now after you cancel? Now you substitute. Remember, conjugate and cancel, and then you go substitute. So now we put the b back in for x. Square root of b plus square root of b is 2 square root of b. With a negative on the outside, makes a. Okay? So, that's it. But like I said, in this whole list of, there's 45 multiple choice questions and 6 free response questions, and I think those are about the only 3 we can do right now. That's okay, we're getting there. But right now, that's kind of where we're at. Or especially that would have anything to do with the quiz right now. All right. So, back to our notes from earlier. And let's go ahead and practice a few of those. We're still going to look at 52 and 54, but those are a kind of a different category from our notes. So let's look at our notes from a few days back. So that kind of covers this a little bit. Maybe it would be a good time to practice a few more limit ones. So let's go ahead and practice we just did a conjugate one. Let's try a factor and cancel and maybe a common denominator one. So let's do, and we already did limits of graphs, right? We just did that problem that had the graphs with the funky piecewise, and we talked about limits there. The cars meet, so we got that. We'll get the tables here in a minute. We just did a conjugate. So let's do a common denominator and a factor one. So, and we'll mix in, while we're doing it, we'll mix in a long way one right here as we go. Okay? So let's do this problem right here. Limit as, no. f of x equals x squared minus x plus 1. Find f prime of 3. Using the definition of the derivative. The definition of the derivative. Feel free to work with a partner or talk with each other if you want to. Now we have the added feature of knowing our shortcuts, right? So we should know what answer we should get, correct? I mean, what's a way to find f prime of 3? Do f prime of x, right? Now that wouldn't work for this problem because I said use the definition of the derivative, right? But what's a derivative of x squared minus x plus 1? 2x minus 1, right? The derivative here is 1, bring the 1 down in front, drop to a 0. So it's 2x minus 1. You put a 3 into that then, you get what? 5, right? 6 minus 1, 5. So you better get 5 for an answer, right? And you know that. So on the quiz, even though you're doing the definition of derivative, now when we first learned the long way, we didn't know about the shortcut, so we didn't know what we were supposed to end up with. But here we would know that we should end up with 5. How do I do what? The shortcut? The power rule. So you bring the 2 down in front, drop that to a 1. So that's 2x. You got a 1 there. Bring that down in front is 1. Drop that to a 0. So x to the 0 is 1. So this derivative is 1. And then derivative of 1 is 0. Derivative of a constant, any constant is 0. So the derivative. And then you plug 3. So you get 2x minus 1. Okay, so here's your setup, right? I always like to write the f notation first. So f of 3 plus h means what? F of 3 plus h means put 3 plus h there and there, right? So put 3 plus h in for the x and then put 3 in for the x, right? So the next line should look like that. So we put 3 plus h in for x. We put 3 plus h in for x. I got to put parentheses around those because I'm subtracting it, so that's really important. Those parentheses are really important. Plus the 1. Then I put 3 in for x, that'd be 9 minus 3 plus 1. Right? Then what? FOIL it all out, right? FOIL it all out in combined terms. So this would be 9 plus 6h plus h squared. This would be minus 3 minus h plus 1. This adds up to 7 over here. So minus 7. So we do all that. So we FOIL that all out. We distribute that negative. The 9 minus 3 is 6. 6 plus 1 is 7. 7 minus 7 drops out. So you end up with an h squared, and a 6h minus h is 5h. So you end up with h squared plus 5h all over h. Which is good, because now, remember, it's factor and cancel kind of thing. So we can factor out an h, and then we can cancel an h, and then we substitute. So we cancel an h, and then we substitute. H plus 5, we put a 0 in for h, and we get the 5 we were looking for. Okay?
Is it okay if we solve for all x and then put the 3 in? Okay with that?
Did what now?
Um,
Oh, if you did
Yeah.
f of x plus h,
Yeah.
so you had x's in here, worked it all out with x's, then put a 3 in for the x there. Yes, that as long as you use the definition of the derivative and went through, that would work fine.
And then I could put any number in.
That's
the
right.
equation and just look at
That's right. That would work. Okay? All right. What's the other one? Common denominator.
it. Just
Okay? Now we won't go through the whole project. Let me just make one up here for you. Let's see. How about 1 over x?
I can see it.
I'm just. How about that? Try that one. Okay? Again, the first thing you should do is substitute. So you put a 3 in for x, you get 1/3 minus 1/3 on top, which is 0. Put a 3 in the bottom, you get 0. 0 over 0 means keep going. So this is common denominator and cancel. Or bow tie, or clear the fractions, whatever you want to call it, or however you want to try. All right. Some of you have got as far as you can go, maybe all the way done. That's good. How many people did kind of a bow tie kind of a common denominator method? Okay. How many people cleared out by multiplying a 3x top and bottom? Okay, that's the other thing I've shown you, which is kind of the same thing. Okay, well, let's look at both of those. Here would be looking at your common denominator, which is 3 times x, and I just multiply the top and bottom by a 3x. So I'll show you both the bow tie also, the common denominator. So if I multiply there, 3x times there, the x's cancel, leaving 3. If I take this times this, the 3's cancel, leaving x. And then the bottom would just be 3x times this. I don't want to multiply that out. I want to leave it like so. Now, can those cancel? Almost, right? And take out a negative. So those can cancel then. And so I end up with a -1 over 3x. Follow the blue here. So I end up with that. And once I've canceled, what can I do? Substitute. So now I can plug in a 3. 3 times 3 is 9. I get -1/9. Okay? So that's one way to do it. Another way to do it would be the bow tie. Or say, okay, I'm going to get 3x as my common denominator. So I'm going to multiply 3 and 3. Or if you just bow tie and go this way, you end up with the 3 up here. And then the x over here. So 3 minus x over this. Common denominator, take that times x and x. So either way, I get 3 minus x over a common denominator of 3x. All over x minus 3. So I invert that and multiply. So I take my x minus 3 up here, invert and multiply. And I have the same thing. I end up with 3 minus x on top. And on the bottom, I have a 3x times a quantity x minus 3. And I can cancel those. If I pull out a negative, I end up in the same place, -1/9. Okay? So common denominator, we're clearing out that. There you go. Those are the algebra ones. Factor, cancel. We did a conjugate one. We just did a common denominator. Okay? All right. So back to those notes. Factor, cancel, common denominator, conjugate. Talked about substitution. We talked about if you get 0 in the bottom, that just does. If you get 6 over 0, that just does not exist. Okay, 2 over 0, something like that. We talked about the graphs already. Let's talk about tables. So that worksheet. Why don't you grab that worksheet that you had today with the calculator limits and some of these. Okay. So I might ask you just a direct question like this one, where you're supposed to use a table as your justification. So what you did is you typed this part of it in, the blue part. You typed the blue part in, except you didn't use h, you used what? X. And so you typed that into your F1. You looked at a table. You looked at as h approaches 0. Now we also had the added feature on this one that this equaled f prime of 3. The a was 3, but the 3 didn't have anything to do with your limit. It was still the limit as h approaches 0 because we wanted the 2 points to become 1. So you looked at that and you looked at that table and saw what you got. Okay, so I'll probably give you some where here's just a limit. Look at show the table, actually write out your table, okay, and do that. So I think we can probably do those problems easy enough. Okay, let me give you one then, kind of from scratch. So I could just write one out and you type in your table. That's not that interesting. Let me give you another one. So go ahead and get your calculators out. Okay, something like this could be the direction. Here's a function. Use the definition of the derivative to set it up to find f prime of 2. But then use your calculator table to solve. So what does that mean? use the definition of the derivative to set it up. Right here, right? This is the definition of the derivative. So I would have limit. Tell me what to put. Well, let's set it up with h, because that's the definition of the derivative, uses h. Now let's be careful here. Let's use the f notation first. I could skip that. You're right. F of 2 plus h minus f of 2 all over h. And you could even use x if you wanted and then put your, oops, not 2, h. Right? Now we could go ahead, now we can take that one step farther because we know what f is. Right? What's f of 2 plus h? Sine of 2 plus h. Minus sine of 2. Now let's stop there a minute. So this is no different than the problem we were just doing, where we got a minute ago, where we got 5. 2 problems ago, right? When we got 5 for the answer. This is exactly the same thing, right? We were saying find f prime of 2. Using the definition, we set it up, we multiplied all those, we squared it, blah, 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 it's distributed negative, and h is canceled, and away we went. Any algebra you can do on this one? You cannot distribute a sign, by the way. Okay? So that's times, and sign is not times, okay? So we could not distribute a sign here. There's no algebra we can do to this. So there's no way we could get the h's to cancel. So that's why I didn't make you. I said just go ahead and use your definition to set it up. And now let's go to our calculator. So what are you going to put in your calculator?
Yeah, with x's.
This with x's, right? So go ahead and do it. Go ahead and do that one. Let's put this with x's. And then we want to look at the table as x approaches what? 0, not the 2. The 2 doesn't have anything to do with it. Well, the 2 does. That's why we have a 2 plus h in there. That's what the 2 has to do with it. But we're doing the limit as h approaches 0. Or in this case, x now in your calculator approaches 0, because now we're putting x in instead of h. But in a problem like this, I'd want to see your setup of your limit. But since you can't do any algebra to this limit, and we don't have a graph of this function, the only thing left is to do a table on our calculators. All right, what are you getting?
6.
Negative 0.416. Now, is that reasonable? Well, let's look at the sine function. The sine function at 2, let's see, this is pi halves, which is 1.57. This is pi, which is 3.14, so 2 be right in here somewhere. Negative slope. Seems reasonable. Oh, but wait a minute. We have the added bonus of already knowing what our answer should have been. We know the derivative of sine is what? Cosine. The derivative of sine is cosine x. So f prime of 2 should have been cosine 2. Go on the calculator part of your, go off the graph screen, go to the calculator part, and type in cosine of 2. And now you have to hit Control Enter so you can get a decimal. Negative 0.416. There it is. Okay? How's that? So, we did a table to find this limit, but it also happened to mean something special about sine and the slope and so forth. But we found this limit, and we set it up, and we used a calculator. All right. So, that's a pretty good, I mean, that's about everything you want to know. Those limits and continuity and how that fits. Now we need to spend a little time with this chart stuff. Okay? in the shortcuts, but we got to be able to do those, I guess. The power rule, basic, bring the power down. So you can make those up all day long and practice of it. So, last thing we need to be able to do here is the chart stuff. A big part of the quiz, those limits, to be honest with you. If you count up total points and everything, limits, continuity, differentiability. That's a big part. All right. So let's go to our homework. Number 52. And we also did, was it 21 in this section? Was that in this section? Or 20? Was 21 we were supposed to, number 20? Okay, and that was a chart, that was like a local max min kind of thing, right? We already did 19, we already done 21, okay? So that's another one of these. Now, but 50, this one's different. I mean, it doesn't seem like it's a local max min one, but it actually is. They give you this function, and this goes a little beyond what I'm gonna ask you, but it's still worth going through because it's got pieces we need to be able to do. They tell you it's what, x cubed minus 3x squared plus k, and they ask you when does this, for what values of k does this have one root, or I think they said x-intercept, same thing, 2 roots, 3 roots, isn't that what it says? Okay. And so this is really a hard problem. This is a kind of problem, though, that we're going to get better at as we see more of these types of things. This is a kind of problem that doesn't seem like it has anything to do with local max, local min, derivatives, anything we're talking about. And all of a sudden we start thinking about what we need to do this problem, and we realize we know how to do everything we need here. But just putting it all together is kind of difficult. First of all, visualize this graph for me. This would be a no calculator problem. Visualize this graph. Kind of a, hopefully everybody's thinking of that sort of thing, right? Now what's the K mean? Some sort of vertical shift. It's a constant. It's some sort of vertical shift. So all of a sudden you put that together with this 1 root, 2 root, 3 root thing, and then you start thinking, oh, okay, this kind of makes sense because this graph could go up like this. How many roots does it have?
1.
It only has 1. When in the world would it have 2? If you shifted it down, in other words, change k. If you shifted it down, how far? Until that's just touching. Then you'd have 2. What if you keep shifting it down? Now you've got 3. Keep shifting it down. As soon as this one bounces or just touches, now you're back to 2. Keep shifting it down. Now you're back to 1. So by thinking of it that way, all of a sudden you realize that you need to know those 2 points. And guess what? Those are local maxes and mins. So this is really a local max min problem. So this is just like number 19, number 20, and 21. Find the local max mins. Well, where do you look? When f prime is 0. When f prime is 0, we want to find the stationary point and do a number line. Now we don't have to do the number line because we didn't have to justify that it was a local max min. So for this problem, I'm going to skip over that part. So we're going to do the derivative, and we're going to set it equal to 0. But this is good practice because this is just like you had to do at number 19, number 20, number 21. And those are more likely the ones that I would ask you to do. Okay? So like 22, I think 22 is another one. You might want to do 22 as one of your practice ones from this being section 2.4. Right? You want to do number 22 or do number 21 again if you haven't got it done. So we set that equal to 0, then what? Factor out of 3x. You get x minus 2. So we get x equals 0 and x equals 2. Oh, so I realize my picture's not very good there. My picture, I'm going to redraw that because now I know where my local max and min are. And I know they have to be a local max and a local min. I know the local max has to come first because I know this is a cubic that goes upward. So my first stationary point is at 0, and then my next one is down here at 2. Okay, so I now know where those are. Like so. Okay, so now I've drawn it so I only have 1 root. Okay, so normally I would do a number line here and so forth, which we'll do an example when we do 54 here in a minute. So I got 0 and 2. So I know my graph has to look like this. So now I need to know when this point is right down here and bounces. How can I find that? How about if I put a 2 back into the original? Because what do I want to happen? I want to get out if it's going to be right on the x-axis, I want to get out a 0. So I need to put a 2 back into here. So I get 8, 2 squared is 4, 4 times 3 is 12, 8 minus 12 plus k. So that's negative 4 plus k. I want to get that to be 0. So what's k got to be? K's got to be 4. So if k is 4, this is going to be just touching, and I'll have 2 roots. So I'll write that down over here. So k is going to have to be a 4. That's one of the times I'll have 2 roots only, when that one's just touching. This isn't, I mean, that's a hard problem. I mean, to see all those things, but as you start looking at it, you start thinking, well, but we know how to do all those things. It's just a matter of seeing that that's what was needed. So what's the other time you have 2 roots? When this one is just touching. So when we put a 0 in for x, we get out a 0 in the original. So we put a 0 in for x, 0 minus 0 plus k, and we want to equal 0. So k's got to be 0. So there's the 2 times you get 2 roots. What about 3 roots? When it's between 0 and 4, right? Because the first time when k was a 4, we got this. And if k is a 0, we got this. So anywhere between 0 and 4 is when you're going to have 3 roots. Because then it'll go like that, right, as you're shifting it down. So k's got to be between 0 and 4 to get 3 roots. So then when's it going to have 1 root? When it's less than 0 and when it's greater than 4. Because when it's greater than 4, it'll be shifted up so far that this one's not touching. And when it's less than 0, it'll be shifted down too far so that the max isn't touching. So that's a really good problem. I mean, that really makes you think through all of this stuff about what's going on. But that's beyond what probably have to do for the quiz. All right, 54. Now this one, all of this process that we go through to do 54 is exactly stuff that you would need to be able to do on the quiz. But I'm not going to probably put it into the velocity, position kind of thing for right now, because this is the first one of these we've seen. This will not be the last by far. Okay? But they give you this function x of t. Kind of weird seeing x as the output. And what is it? Read me the function.
3t to the 5th. 25t to the 3rd. Plus 16t.
All right. Now, we have to imagine what's going on here. Really, guys, this is like the Bismarck, North Dakota problem. East and west. We got an x-axis. Pretend there's an x-axis painted on the floor here. So at 0, so my position over here, I do positive position, 1, 2, 3, 4, 5. Over here, negative 1, negative 2, negative 3, negative 4, negative 5. Okay? This is really a position, velocity, acceleration problem. Position, velocity, acceleration. It's just that I'm going to call my position graph x here, since we're on the x-axis. Okay? My velocity graph would be x prime then. Right? We got to get over the fact that x can be an output here. T's the input. Question or just? Right, okay. So, what would it mean if I asked for x of 2? You'd put a 2 into here, right? Okay, and let's say you got out a 7. What's that mean? X of 2 equals 7.
You're on 7 on
At 2 minutes or seconds or whatever, I'm at 7 on the x-axis, right? That just means where I'm at. But the question asks what? When are you moving left? When is a particle moving left? Well, the Bismarck problem, that's like moving west. So what is it really asking? When is the slope negative? When is x prime negative? That's when x is decreasing. Well, think about that in the chart, right? Well, decreasing, that's when you're moving left. Think of my position. I'm out here on the number line at 10, 9, 8, 7, right? My position is decreasing, right? So my velocity is negative. I'm moving left. And if you're over here, negative 1, negative 2, negative 3, negative 4, those numbers are decreasing, right? So when you're moving left on the x-axis, your position is decreasing. So in the chart, decreasing is when x prime is negative. That's why we do the number line, right? That's why we do the number line. So what we need to know is when x prime is 0, right? To find out when x prime is negative, you want to find out when it's 0. That way you can check in between and see when it's negative and positive. So we do the derivative. Here's good practice on our power rule. So what do we got? 15 t to the 4th minus 75 t squared plus 60. And we want to set that equal to 0. Okay, oh geez. How about we factor out a 15? We have t to the 4th minus what? 5t squared plus 4. Right? Equals 0. Well, 15, this factors, doesn't it? T squared and t squared. Minus 4 minus 1. Oh, we got to keep factoring. T plus 2, t minus 2. T plus 1, t minus 1. A little more complex than I would give you on the quiz, probably, but you get the idea. Definitely. And you go through there. Now, one thing we can't forget is in the problem they said t is positive. T was time, so we're going to start at time 0, so t is going to be positive. So we can throw out a couple of these negative ones, right? So what are we going to have? T equals 1 and 2, right? We can throw out the negative 1, so forth. So t equals 1 and 2. Those are my stationary points, which means what for the particle? See, this problem's got context to it. What did we just find? At 1 and 2, it's not moving. Particle's not moving. It stops. Stationary points, right? So at 1, now what might it do when it stops? Might turn around or might keep going, right? What would that be if it went to the right, stopped, and kept going to the right? That's an old flat spot when we were doing graphs, right? But it might go right, might go left. So see, this is a local max min, flat spot kind of chart kind of question, but it's in the context of velocities. All right, so what do? We do a number line. Just like we did on 19, 20, 21. We put 1 and 2 onto a number line. And we got x prime is now, so this is when 1 and 2 is when x prime is 0. We want to find out when x prime is negative. Because when x prime is negative, that's a velocity. That's when this particle is moving left. Okay? So a local max would be kind of like when it goes right and goes back to the left. That'd be kind of like a local max. Positive then negative. Or local min, it would kind of go left, go back to the right. Okay? So that's the connection here. All right, so we need to put in something like, well, we're supposed to keep t positive, so maybe we'll put in a 0.5 here. Maybe a 1.5 here. Maybe a 3 here. Oops. Here. Put a 3 in there. And where do we plug those? X prime. That's not a lot of fun. How about this one right here? This would be a better X prime to plug into. Okay, let's plug into this one. Okay, so 0.5. Well, let's see. That's positive. 0.5 plus 2, that's positive. 0.5 minus 2, that's negative. 0.5 plus 1, that's positive. 0.5 minus 1, negative. I had 2 negatives. That's positive. Put 1.5 in, that's positive. 1.5 minus 2, that's negative. 1.5 plus 1, that's positive. 1.5 minus 1, that's positive. What I had 1 negative there in there. Now let's put a 3 in. Positive, 3 minus 2 is 1, that's positive. 3 plus 1 is positive. 3 minus 1 is 2, that's positive. They're all positive. So there we go. So what's this particle doing? Right, left, and right. So the answer to the question, when is the particle moving to the left? Between 1 and 2. Between 1 and 2. Time units, whatever, seconds, whatever it is. Okay? So I'm not going to give you one in those terms, but I might say here's a function f, find the local max and min, find where the function's increasing or decreasing. You would do everything the same. You would do the derivative, set equal to 0, you would factor it, you would do a number line, you would find the plus or minus. Here's where the function's increasing, here's where it's decreasing, here's a local max, and then remember that's when we have to explain it. Local max, f prime goes from positive to negative, so f goes increasing, decreasing, right? That's local max, that'd be local min. Everything would be the same. The only difference is this time it had a context attached to it of position and velocity. All right, so if we go back to our thing, our worksheet here, that's the chart stuff kind of problems. Number 19, if I pull up the notes from Friday, we did number, or did we? No, that was 2 days ago. That was on the 14th. We did problem number 19 on page 121. Here we got a function. We were supposed to find where it was increasing, where it was decreasing, where it had a local max, where it had a local min. We did the derivative, set it equal to 0. Factored it out. Found our stationary points, did our number line. And there it was. So you could do number 22, be good practice for that. You had number 20 today. Was it 20?
Yeah.
20? Okay. Okay, what, and of course you can always look them up here in the back. And you got a little bit of time to do that here. Number 20, what was it? Increasing from 0 to 1. Is that correct?
Or maybe the classes.
Number 20, 0 to 1. Increasing from 0 to 1, decreasing before 0 and decreasing after 1. Local min was at 0, local max was at 1. Okay? And so again, you can work on number 22 as well. So that's it. That's it. Plenty. Any question? We got a little bit of time here. Is there any, as you think back through this, any other questions? Yes, Cal.
On number 54, the problem didn't specify whether it was moving right when it was positive, or whether and right positive, left negative, or vice versa. So that time we assumed that it was moving right when it was positive.
It did kind of say it actually, in the sense of the numbers, they said it's an x-axis. But yes, it's safe to assume that up is a positive and down is negative, and right is positive and left is negative. But here's why I did say it, and it goes to what I was saying when I was marching back and forth here. If this is the x-axis, when it is going, when the particle's moving left, its position is going 10, 9, 8, 7, its position is decreasing. Or it's going -1, -2, -3, which is also decreasing. And according to the chart, if its position function is decreasing, its derivative function is negative. So that's how you would know. That's how you would know. And same thing, sometimes when it wants to talk about up and down, it'll say a particle on the y-axis is moving, okay? So we use the x and y-axis just because those are marked things, okay? Other questions? Other questions? All right, so, well, I have no specific homework assignment for you other than to review for the quiz. So, you know, these notes from, well, that we looked at, you know, here, those notes from a few days back. This was from the 14th as we went through this stuff. You know, a long way, so we went through those. We went through some examples today to review those. We got all this stuff about limits here. So these are on the website from the 14th. Then we said the chart stuff, and then the notes from Friday, the 15th, we added in this, you know, all of this that we went through about the 3 different ways that a function is continuous, and if it's discontinuous, why, which one of those 3 reasons caused it to not be continuous. We talked about a function being differentiable. We worked on problem 66 and 67, so revisit those. That's, I mean, you know, that, the notes here on the 15th have this example of the chart stuff. Number 21 here is a good example of that. And then you got your worksheets. Your worksheets gave you some good examples of algebra limits. So that first worksheet you did, we went through those today, the table, we went through the table. That's it. You can do all that stuff. You can go over. All right. You need to check any other homework problems or anything before you go. You got the answer books here. If you need to ask me anything, please do. I did see a few problems in. I guess if you really wanted something new to do, this is not by any means comprehensive. This is. I went back and I went through the review. I went back through the review section, which is on page 150 and 152, 150 to 152, and I found a handful of problems that do have something to do with the quiz. I mean, so those, if you're looking just for something new to kind of make you think about something, those could be a few, but it's certainly not a comprehensive list by any means. Pretty much need to go back through your notes and back through your homework problems. And, okay?